Welcome. Today we're going to tackle a problem that looks challenging, but we'll see that by using a few key properties of logarithms and exponents, we can solve it systematically. We'll be solving this logarithmic equation. By the end of this video, you will be able to solve complex logarithmic problems by making a clever substitution and using the laws of exponents. Our goal is to find the value of x that makes this equation true. Let's start by introducing a substitution to simplify our equation. This is a common strategy in algebra. We will let the entire left side, log of x squared, be equal to a new variable, m. This substitution helps us break the problem into smaller, more manageable pieces. Remember, the log function, without a subscript, implies a base of 10, so we can rewrite this as log base 10 of x squared equals m. Now, let's convert this logarithmic equation into its equivalent exponential form. The definition of a logarithm states that if log base b of y equals x, then b to the power of x equals y. Applying this to our equation, we get 10 to the power of m equals x squared. So, we have our first important relationship, 10 to the power of m equals x squared. This is our first stepping stone. We've taken the logarithm and turned it into something we can work with more easily. Now, let's use the other part of our original equation. We established that the right-hand side of our original equation is m. This gives us a simple linear equation, relating our new variable m and our original variable x. From m equals x over 25, we can easily solve for x by multiplying both sides by 25. This gives us x equals 25m. And with that, we have our second key relationship. We now have an expression for x in terms of m. We now have two equations. Our next step is to combine them to eliminate x and solve for m. We have 10 to the m equals x squared and x equals 25m. We can substitute the expression for x from the second equation into the first. Let's perform that substitution. So, we replace x squared with the quantity 25m squared. This gives us 10 to the m equals 25m squared. Now we can expand the right side of the equation. 25m squared is the same as 25 squared times m squared, and 25 squared is 625. So our equation becomes 10 to the m equals 625m squared. Look at what we've accomplished. We've transformed our complex logarithmic equation into a more standard exponential equation. Our problem is now to solve for m. Solving the equation 10 to the m equals 625m squared directly is difficult. We need to find a more elegant approach. The key here is to manipulate the equation so that we can compare the powers of the bases on both sides. Let's start by rewriting our equation. We're going to break down the bases, 10 and 625, into their prime factors. 10 can be written as 2 times 5, and 625 is 5 to the fourth power. So our equation becomes 2 times 5 to the m equals 5 to the fourth times m squared. Now, we can use the law of exponents that says a times b to the power of c is equal to a to the c times b to the c. Applying this, the left side becomes 5 to the m times 2 to the m. So our full equation is 5 to the m times 2 to the m equals 5 to the fourth times m squared. Notice the presence of the number 5 on both sides. This is a very powerful clue. Our goal is to find a value for m that makes this equation work. Let's make an intelligent guess. We have 5 to the m times 2 to the m equals 5 to the fourth times m squared. Let's consider the powers of 5. On the left side, the power is m. On the right side, the power is 4. What if we make the bold assumption that the powers of 5 on both sides are equal? If the powers of 5 are equal, that means m must be equal to 4. This is a hypothesis. It's not guaranteed to be correct, but let's test it. If m equals 4, does the entire equation hold? We substitute m equals 4 back into our equation. This gives us 5 to the fourth times 2 to the fourth equals 5 to the fourth times 4 squared. Let's simplify. 2 to the fourth is 16, and 4 squared is also 16. So we have 5 to the fourth times 16 equals 5 to the fourth times 16. The equation is true. Our hypothesis was correct. The value m equals 4 is the solution to our complex exponential equation. We've successfully solved for m by comparing bases. We're not quite done. The problem asks us to solve for x, not m. So, our final step is to use our value for m to find x. We found that m equals 4. Now we use our second relationship from earlier, x equals 25m. Let's substitute m equals 4 into this equation. This gives us x equals 25 times 4, which is 100. And there you have it. The solution is x equals 100. Now, let's quickly verify our solution by plugging x equals 100 back into the original equation. The left side is log of 100 squared. The right side is 100 over 25. Let's simplify both. The left side becomes log of 10 to the fourth. The logarithm base 10 of 10 to the fourth is simply 4. The right side is 4. Since 4 equals 4, our solution is correct. We have successfully verified our answer. So, let's recap the strategy we used to solve this seemingly difficult problem. First, we made a strategic substitution, setting m equal to log of x squared. Second, we converted the logarithmic equation into its exponential form, and then used the linear relationship between m and x to create a complex exponential equation. Third, we used prime factorization to break down the bases, and then compared the powers of a common base, the number 5, to find our value for m. Finally, we substituted that value back into our linear equation to solve for the original variable x. This problem is a great example of how you can combine different mathematical techniques, logarithms, exponents, algebra, and number theory to find a solution. Thank you for watching.